Hi, and this is measuring the rate of reaction. And we've put on here lots of different pictures about measuring the rates of reactions and ways of doing it. And a small picture of a man and his dog, just because we've been very cat heavy in the YouTube clip. So we've now got a dog and it comes with its own man. Meanwhile, back in the land of revision, here I'm just going to go through the pictures about how you would use these to measure the rate of reaction. So here is a simple one. What's happened here is you've got some acid and some magnesium, and they're reacting together to produce the hydrogen gas. And you are collecting the hydrogen gas in this measuring cylinder. What you would have done first is filled the whole thing with water, and as the hydrogen gas comes through here, it goes into the water and pushes the water out. So the amount of water that's pushed out will equal the amount of gas that you've produced. Now, if you have a stopwatch going, then every minute you can record the reading on the measuring cylinder, and that will give you a nice indication of the rate of the reaction. This one here is the same. So we've got a gas being produced. It goes up here into a gas syringe. So that's rather than going through water, this is the gas that's collecting here is pushing the plunger out. And again, you would record your results off here with a stopwatch. So every 30 seconds or whatever, you would then write down the reading on the gas syringe. This one here, this one relies on a gas being produced in a reaction, and what you do, although this here, we've got our conical flask, which is empty, we've got this on 0 because it's been tared, that means it's been zeroed, so that it's not weighing the conical flask. You'd put your reactants in, and then you would measure the mass of this over time. As the reaction continued, the gas would escape, so the carbon dioxide or hydrogen would escape from here, and therefore the reading here would drop. And you'd just write down the reading over time. So every minute or 30 seconds, you'd write down what it says. Again, only works if something's escaping from it, otherwise it's not going to do anything. Another really common one that we're going to look into a bit more detail is this one, where you've got your reaction happening in a conical flask over the top of a cross drawn on a piece of paper, and you time how long it takes for this cross to disappear. Now this one here is used, you can't really use it to measure the progress of a reaction, but it's used to compare different reactions. So these ones can measure a progress of a reaction over time, and this one is to compare. Now, what sort of things would you get? Well, this sort of graph, panic, I don't think you've ever been asked to draw it, but you might need to say what it means. So if we look along the bottom here is time. Oh, it's copyrighted, don't report me. Right, there's the time. And here is the concentration of the reactants and the concentration of the products. And you can see as time goes on, the concentration of reactants is going to decrease because they're all reacting to form products, so the products are going to increase. So you get this sort of graph. What's happening here is that these reactants, let's cover with it, these reactants here, the pink ones and the blue ones, they react together to form a new product, and that's what you're recording on this one. We'll go into more detail in the next slide. So here is a typical graph, and a typical question would be about explaining the shape of this graph. First, they might say describe it. Don't go wrong here. Describe it means between 0 and 4 minutes, the loss in grams is increasing steeply, and then between 4 minutes and 7 minutes, no more gas is produced. Now, the reason why it's quick at the beginning is because all the particles here, there's loads of reactions that can go on because there's lots of pink and blue ones, so it'll be quick reaction. As time goes on, they will react, and quite like that really, but they'll do. So they react, therefore the reaction will slow down because there's not so many products, there's not so many reactants around to react together, so there's going to be less product made. So this here slows down as more and more product is made, and it's less and less likely to collide. So these particles here are less and less likely to collide successfully because there's loads of products made. They're all in the way, and there's less reactants to react. At this point here, the reaction is finished. Look, there is no more loss in grams. That means that that's it. Everything has totally reacted. So that is the mass following